we will try to determine the electric field intensity. Due to a circular line charge. Here, let us consider a circular line charge of radius r1 . So here the line charge is distributed along this circle of radius r1, and let us say the charge density is lambda L coulombs per meter. So due to this charge distribution, we'll try to find out the field at a point P. So let us say this is given by the position vector r. So here r is given by ZAZ, because the position of point P is 0, 0, Z. So determine the electric field at this point P. Due to this entire line charge, we will consider a differential line charge. So here the length of this element is r1 d phi, and the charge within this element is given by lambda L to dl. So here this is r dash, and here r dash is given by r1 a rho. Now we will try to find out the electric field dE at P due to this differential charge dq. So this is given by dq divided by 4 pi epsilon naught Okay. Now we see that here the electric field dE has so here r minus r dash is given by that is the vector r minus r dash is given by ZAZ minus r1 a rho. So therefore the magnitude of this vector is given by square root of z square plus r1 square. So now we can substitute this here, and we get this vector ZAZ minus r1 0. So if you observe the electric field at this point P due to this differential charge dq. So this is the electric field. So this electric field has rho component and also z component. So this is the z component and this is the rho component. Now we see that due to the symmetry of the charge distribution, the rho component at this point P, that is this dE rho, is cancelled by the rho component of the electric field at this point P due to this differential charge, which is symmetrically opposite to this charge. So because of this, in the net electric field, the rho components are 0. So therefore, the electric field E is given by integral of dE, and since the charge is distributed from phi is equal to 0 to 2 pi, we will integrate along 0 to 2 pi, and we will consider only the z component. So upon integration, we will see that this will result in 2 pi. This gets cancelled with this 2 pi, and we will be having the expression for the electric field at the point P due to this circular line charge is given by this expression. To derive the electric field at this point, that is, if we take the point to be at the center, if we want to determine the electric field at this point, which is the center of the circle, then z is equal to 0. So we can see that at the center of the circle, the electric field is 0.